Hello, welcome to this video. Today we're going to look at this problem that was recently on someone named Mike Boyd's channel, where he showed how difficult it is to get into the Oxford University in the subject of math. So, and one of the questions he did to prepare for the interview part is as follows. Suppose you have a pizza and you make n cuts to the pizza. So in this case, we made 5 cuts to the pizza. What is the biggest amount of slices or regions you can have? So in our case, I counted this up earlier, we have 16 regions. And the question is for any general amount of n cuts, a closed formula for the biggest amount of regions. So let's first of all try to understand how a new region is created once we do a new cut to the pizza. So let's say we're going to do this cut. We start here, and notice right when we hit a line is where we separated this region into 2. So we added one more region. Now we sort of entered a new region after passing this line, and once we hit another line, again we have a new region. A new line, a new region, and at the end we hit another supposed line, but it's not one of our lines, you can think of as the pizza crust. As we hit it here at the end, and we hit it here, and even though it's not a cut, it's still sort of a line of this region, meaning that once we hit it, we did indeed separate into a new region. So in total, if I do n plus 1 cuts, so I did n cuts, and now I'm doing the n plus first cut, the maximal amount of regions I can have is the original one, plus the biggest amount of lines I'll be able to hit with my n plus first line, which I'll call it n, mn, and then plus 1, because don't forget, we're hitting a new line that isn't ours, it's the pizza crust, so we need to add 1 to the amount of lines that we hit inside the circle. So we want to find a closed formula for an, so now all we need to figure out is this mn. What is the biggest amount of lines I can hit, such that I'll be intersection point, the biggest amount of lines I can hit within the circle. So let's ignore the circle for a second. Let's imagine we have some configuration of lines here. And let's suppose we run a new line through this. If the new line doesn't have a slope equal to all the slopes of these lines, it means it'll eventually hit every one of them. Because of course any two lines with a different slope will eventually hit each other. So we pass a new line. And let's assume that no 3 lines are intersecting at one point, because if they would, we can just move a little bit to one of those lines to make it so that no 2 are touching. So now we have this, but what if our original circle was, say, this one? How can we ensure all of the intersection points are still in the circle? Well, let's understand how we want what property we want our lines to have. We want it so. Because we want it, the way we build each cut is that it hits each previous cut, or each previous line. It means that any 2 lines intersect inside the circle. So if we do this, say, by induction, we start with assuming n n lines with all the intersection points inside the circle. Can we always draw a new line that will intersect all n lines with all intersection points being in the circle? So let's show that we can. And here's what I'm gonna do. So this is how I'm gonna do it. Let's have some configuration of lines. Now, draw any line you want, as long as its slope isn't equal to any of these slopes, and it doesn't intersect in any of these intersection points. And so basically, an infinite amount of options. Let's pick this line. Now what we can do is, well, maybe the circle is like this, and it doesn't fit all of them, but what we can do is, because all the original intersection points are inside the circle we want, if we start making all these lines get closer and smaller, if we start shrinking our system, all the original intersection points will still be in the circle because they already were. If we're shrinking them relative to the center of the circle, they will still be in the circle, but the amount of regions won't change until we get a new intersection point inside the circle. And we'll be able to shrink it down until we have all of the intersection points inside the circle, like so. Imagine it's a circle. So effectively, the original circle was something maybe like this, but what we did was shrink the shrinking down from a different perspective. Increase the circle size such that all the new intersection points are now in the circle, meaning that we did show what we want. We've shown that for any configuration of n lines, you can always draw another line that will hit all of them and will still be in the circle. You just have to shrink the system. But we don't care that we changed a bit the configuration of lines, as long as the amount of regions increased in the optimal way, which it did, we're good. So now we know this mn, which is the biggest amount of lines I can hit whilst still being in the circle, is n. So now we just have a simple reduction formula. an plus 1 is equal to an plus n plus 1. We want to find an. Well, first we also need an initial condition, which is a1. What's a1? Well, if you have a circle and if you have a pizza and you do one cut, you're going to have, the best you can do is 2 regions. So a1 is equal to 2. So now let's just find an. So I'm going to write an like this. An is an minus 1 plus an minus 1 minus an minus 2, and so on until plus a2 minus a1. So it's the sum of the differences, and then plus a1. So we can easily see how all of this will cancel down to just an. This with this, all the way down. But now we know what each of these is. We know, first of all, a1 is 2, but then we have a sum that goes. This k goes from 1 to n minus 1. We have the sum of ak plus 1 minus ak, which is k plus 1. Now, this is 2 plus. Now, the sum of k goes from 1 to n minus 1. To n minus 1 of k is n times n minus 1 over 2. And the sum as k goes from 1 to n minus 1 of 1 is obviously n minus 1. And if you simplify this a bit, you eventually get the final result as n squared plus n plus 2 over 2. And just to check, just to make sure that it's good, let's check it. So first of all, for 1, we should get 2. 1 plus 1 plus 2 over 2 is 2. Let's check it for 2 lines. For 2 lines, the best I can do is 4 regions. Here we'll get 4 plus 2 plus 2 over 2, which is 4. And just as one final check, for 3 lines, we have 1, 2, and another 3. And notice we can already see this is optimal because each 2 lines intersect inside the circle. And here we have 1, 2, 3, 4, 5, 6, 7 regions. And if we plug in the formula, 9 plus 3 plus 2 over 2 is indeed 7. And you can keep checking and you'll see that this formula still holds. So finally, that's it. If you want more content like this, please subscribe to my channel. I'll be uploading more interesting content and videos like this in the future. And finally, that's it.